Hello again, TFAS. Onward in this lecture, I'm going to talk about noise. And noise is an issue with analog gear. It always has been. You can kind of break it up into three different types of noise. You've got hiss, which is high frequency, typically white noise, stemming from random electron movement. Hiss was always a big part of analog tape. Vinyl records also have hiss. Hum, we all know what hum is, usually a single pitch or a couple pitches. It's usually low in frequency, typically related to AC power's 60 hertz oscillation. You might hear harmonics of it, like 120 hertz, 180 hertz, etc. Buzz is typically multiple frequencies at once. It's really distracting and really annoying. It may or may not be related to the 60 hertz power. It could be coming from RF sources and that sort of stuff. Hum and buzz can come from a lot of different things. It can come from grounding issues, ground loops and all that, and I'm going to discuss that in another later, a couple weeks from now in TFAS. But it all can also come wirelessly, like through the air, electromagnetic interference, and it can come from a lot of places. Motors, generators, radio transmission, neon lights, fluorescent lights, power cables, transformers, motors, light dimmers. All these things can emit wirelessly noise, electromagnetic noise that can induce into your wires and into your cabling and into your audio gear. And so well-designed cabling and well-designed systems do everything they can to avoid noise. I keep talking about electromagnetism just to kind of clarify what that is. It's a broad term. It's both electric and magnetic fields that are typically oscillating. Magnets, of course, emit a magnetic field, and electrically charged objects emit electric fields as well as magnetic fields. And as we've talked about in class, current through a conductor radiates a magnetic field and an electric field. And the speed of this oscillation of this invisible energy, electromagnetism, is energy transferring through a medium. I mean, light is electromagnetism, X-rays are electromagnetism, radio waves, all these things. But we classify the frequency of oscillation and put it into different categories. Very, very fast, therefore very, very tiny waves are gamma rays. These are the ones that give immediate cancer, if not kill you. X-rays, you can see through the body. Ultraviolet light, give you a nice sunburn. Visible light's even lower in frequency. Infrared light is even lower. Microwaves cooks your hot dog there, and of course the radio waves are even lower. And these things are oscillating in the radio waves are in the thousands of hertz, all the way up to the millions and billions, and even higher of hertz. So very, very high in frequency. And hum and buzz are typically side effects of electromagnetic energy being induced on our gear. And it can come from a lot of places. Radio stations, which of course we have a big tower outside NESCOM, can provide all sorts of stuff. And even if the frequencies are very, very high, far above the audible band, they can get into our gear and they can demodulate into lower frequencies. So that can be a problem. Hum, if you lay an audio cable, specifically an unbalanced cable, over a transformer, like a power transformer, that can put a nice 60 cycle hum in your audio gear. So well-made cables and well-designed balanced circuits can avoid that. Backstage at a show, look at all that power cable. A lot of that's feeder cable. A lot of that is single conductor power cable. That's going to, create all sorts of magnetic fields that if you put your audio cabling across this, you're asking for some challenge. Motors, lighting, all of these things. So how do we deal with electromagnetic radiation? How do we deal with this energy? And and I'm going to be clear about that. I'm going to be specific about this. Inductive coupling, when the energy is coupled into nearby cables, when you run a mic cable over this massive pile here, and the energy is induced as hum and buzz on the cabling. How do we get away with it? So we're going to explore a lot of these in class at greater length. Some of these things are I'll bring up this slide multiple times over the next couple of weeks. But I'm going to go over the list right now. First thing is distance. Electromagnetic energy follows the inverse square law. What does that mean? That means the farther away you get from a source, the lower in amplitude that magnetic field is. or that electromagnetic energy is, the quieter it is. So, move your audio gear away from your transformers motors and, other things. When years ago, when I was an audio student at Berklee College of Music, we were totally obsessed about, running all of our lines, our headphone lines far away from our mic lines and at right angles and all this stuff. And that you don't really have to be that ridiculous about it, especially because balanced lines and common mode rejection, which we have not talked about yet, can get rid of most interference. But keeping stuff away is a good idea. In this picture here, you certainly wouldn't want to run your low-level mic cable over the top of that pile. Angling devices is a good thing sometimes if you're picking up a lot of hum, buzz, or radio stations. If it's a particular object, move that object and angle. I'm going to just jump ahead for a moment. The classic example of this is a guitar player sitting in a studio. If you had a conventional television set, today our computer monitors are LED, obviously, but you still might have gear in the room that's radiating out a magnetic field, and you have to move the guitar player. You have them change angle by 90 degrees. So I'm face a different direction and the hum and buzz goes away. This is a problem that's specifically prevalent with single coil pickups like a Stratocaster or the P90 pickups. They're famous for their picking up every hum and stray magnetic field. So moving the guitar player around, sometimes you got to tape the guitar player's feet to the floor or put markers on the floor and say, dude, you can't move from this position. So this is a common thing in the control room we deal with, is trying to, avoid magnetic fields by moving. And sliding into some other things, and this is what we're going to talk about in the next couple slides, is shielded cabling. Shielded cabling might reduce the electric field, at least the higher frequency noise, the higher frequency hum and buzz that's electromagnetic. Shielded cabling might help that, and I'm going to talk about that in a moment. Balanced interconnections, which we'll talk about in class because it's really important in audio gear, do a lot of good in this arena. And avoiding loops in power cabling, you already know that when you loop a conductor on top of itself, it multiplies the magnetic field. It will also multiply the reception of a magnetic field. So, avoid piling all your cables up in a loop. And some people, in some power devices, you actually have to loop in figure eights because that interferes the magnetic field. So, and one last thing you can do here is better gear typically is better shielded. When you spend more money for a pro piece of audio gear, it's made of metal, it's got fancier, it's just designed better, and electromagnetic transmission is more reduced because it's a better piece of gear. Anyway, I'll do this the shielding slides on another video, and we'll stop right here. Okay, see you soon. Bye-bye.